Today's lesson we're going to discuss graphs of logs. This is in the book on page 16. Logarithmic functions. This is 1C. It talks about asymptotes. What else? It talks about this symmetry. I'm mostly interested in this one here. So this is an exponential curve, and this one is a log curve, right? And that's a pattern that you get when you have inverse functions. So they reflect along this, what do you call that, diagonal line, y equals x line, which shouldn't be too surprising because basically what's happening is the x's and the y's are swapping around. So I'll show you what I mean by that. And I think we might use natural log. No, maybe we'll do base 10. So if we had an exponential, and I was to graph it, I've got my y and my x, whatever base I'm in, the shape's going to look pretty similar. Okay. So let's say it's y equals 10 to the power of x. Y is the answer that we're getting, but x is powers, right? Now, if I graph y equals log x, can fit that here. We cross at 1, although this time it's in the it's an x-intercept. Whoopsie. All right, there we go. Should put little arrows on my curves. Good. So this is y equals log in base 10 of x. I'm going to take this and rewrite it. So what we're saying is in base 10 with power y, our answer is x. Now I want you to compare this one, this statement or equation, to this statement, and you should be able to see that the x's and the y's have just swapped places, right? So these are equivalent things. This is just a rewriting of the log statement. So 10 to the power of y equals x. What we've got here is our powers are y values. And over here in the exponential, our x's were our powers, right? I think what the book does, it says you could rewrite this as a log statement. So yeah, why not? So we could say log in base 10 of our answer, which would be a y, equals x. And again, you can see x's and y's have swapped between these two, right? So you can then imagine what that's going to look like graphically. I'll show you the picture. Like this line here, if you were to swap your x's and your y's, you get this reflection, I guess, about this diagonal asymptote along this y equals x line, right? Okay, if I go back to my picture and just quickly discuss horizontal vertical asymptotes as well. Undo here. So in our log graph, you do have a vertical asymptote, okay? Because what's going to happen if you try and put in 0 or a negative number into your log, you're going to get an error. You can't do that. Maybe we can see it here more clearly. It's like what possible y value could give us a negative answer, and the answer is there is no y value. Negative, fractional, whatever. I can't get negative answers, so I can't log negative numbers. In fact, I think in specialist maths, they often actually write the x, depending on the context of the question, but they might be writing the x inside modulus symbols. Although in methods it doesn't matter. Now, horizontal asymptote does not exist for this log graph. Right, these values will go up very slowly forever. We're graphing powers, so they're going to go up very slowly. If I put in x is 10 here, I'll get 1 as my y. So this is going to increase very slowly. By the, when we get to a power of 2, we're at 100. So if I could go off the page for another 30 centimeters, right, 100, that's where the y will be 2, but it will just keep going up slowly. And here you can see this theoretically goes down, indefinitely, as opposed to an exponential graph that does have that horizontal asymptote along the x-axis here. So the log graph's got a vertical asymptote. We could write it as x equals 0. Vertical asymptote. Right, I just wanted to discuss one more idea. If I was sketching a log graph, I might make some room. No, I want to keep some of that. Let me try this. It might be useful to do it in such a way that I modify the way I would normally do a table of values. So normally if I wanted some points to sketch, I'd set up something like this, right? We've all seen tables of values like that. But if I'm doing logs, I actually put those values into the y's. Right? So I'm again using this idea that I'm graphing powers, like the output of the function is powers. Logs give me powers. And so I might be interested, well, where do I get the power minus 2, minus 1, 0, 1, and 2? So in terms of a table of values, it can be quite helpful if you're graphing logs to set them up differently like this and put whole numbers into your y's and think, well, right, minus 2 equals log in base 10 of, x. Or how do I get that? Okay, maybe we could think of it this way. Right, and say, all right, well, what's 10 to the minus 2? That's 100th. So on this graph here, it'd be hard to see, but at 100th, right, I'm down at minus 2. My sketch isn't that accurate, but and minus 1 would be at a 10th, right? So if I did the same thing with minus 1, I think, well, how do I get this power of minus 1? So as if I was logging 1/10, right? What about 0? How do I get the answer 0? Be the next one. And that's the same for any base. So how do I get this 0? what would my x have to be? Well, I'd have to have 10 to the 0. And what's 10 to the 0? It's 1, right? So I would have to be logging the number 1. Now that's true in any base if because most of the time you're going to be doing natural log graphs. So this number is 1. When we get to our power of 1, hopefully that's fairly obvious. Maybe I'll give you an example where I've got 3, right? So my function y equals log of x. I'm thinking, well, how do I get this power of 3? Very easy to see if you use base 10 in the index. You go, all right, well, there should be an x there. Hasn't come out right. All right, well, that number's 1,000. Okay, so if I wanted to put that point on, which I wouldn't because it won't fit on the graph, but I could go out here and my x is to 1,000 and then plot the point. X is 1,000, y equals 3, and do my graph that way. So just wanted to show you that tip of graphing in powers or setting up a table of values. It can be quite useful for graphing. Okay, now the book suggests that you go and graph. Oh, it has a graphing package. Where is that? Let's have a look. Logarithmic graphs. Now you can probably just do this in Desmos. So they've got some number out the front of the log. They've got this translating the log left and right, and then they've got a multiple of x as well. So why don't we just type that into Desmos? You can do it at home. Desmos calculator. So y equals, they've used the letter k, natural log. Desmos will see what I'm doing. And then they had b brackets x minus c. Yep, good. That's what I want. So if we leave it as just log x, our b will have to be equal 1, our c would have to be 0. All right, so you want to think about your most simple curve first. Can I draw? No, I can't. I need my pen back. There we go. So we are graphing y equals log x. It's natural log. You'll see that this is still 1, right? Just like it was in base 10. If I was trying to plot this by hand, I'd be thinking maybe I need a few points to plot. So I could set up a table of values here. Apologies about that line. Maybe I want to think, I don't know, where do I get minus 2? Where do I get minus 1? Right, remember that our y values are powers. Okay, that's the output of this equation. This is equivalent to saying we're in base E. We're using powers of y to get x values. Right? So that's why I'm doing this table of values in reverse order, and I might think, all right, well, what happens if I've got minus 2 here? E to the minus 2, it's this, isn't it? Well, e to the minus 1, 0 is 1. This will be e to the 1, and this will be e squared. Right, so just need a cursor back. See if Desmos is smart enough to show me those points. So if I can find the 1, it's about here. Come on. Oh, it won't let me go there. It's like flipping. I thought it might say E for a minute, but it doesn't. Oh well. But you could see it was pretty close to E, right? 2.718, oh, 2.72, yeah. And so that's what I'm showing here. This way I would have a few points that I could plot if I needed to, right? 1 on E's down here. Yeah, no, it's not going to show me E's. It's just giving decimal approximations. Okay, so I'll just make some room and then we'll start doing some modifications to the... It's always good to just learn inductively like this. So you're wondering what happens to a graph? Well, just start drawing graphs and see for yourself. And you've done this before, right? Whenever we introduce graphing a new type of function, at least in my class, we just want you to go and graph a whole lot and see what happens, right? So maybe we could look at this k. I want to make this k value fairly large to begin with. And hopefully it's not going to surprise you that it's sort of blowing up the curve there, because all of your log values are now going to be multiplied by some larger number, right? Maybe it'll go up to 5. You can see, so there's a shape change. Maybe you call it a dilation of that curve. Okay, what about this b value? All right, we sort of get a similar thing happening. It's not as pronounced. But, you know, that is happening. You'll notice that time the x-intercept changed. Right here, the x-intercept is not changing when I change that k. All right. If I modify this b value, though, it does. I might just go back to the k for a minute, because we could think about, with k, we can think about, well, what happens if we go negative? You'll see in a minute. Hopefully this won't surprise you too much. So I've made it -1. That's going to take all the y values that I was getting and make them minus of each other. So I might just quickly swap between. So there's our regular y equals log x, taking on this shape. You can imagine everything flipped about the x-axis, or reflected about the x-axis, if I just whack a minus on there, right? Because all these y values have, all the negative ones have now become positive, all the positive ones have become negative, right? If we then blow this out, I had it at 5 before, let's make it -5. Yeah, similar shape, but upside down compared to this one here, right? So please do this. Go have a play with the curves, get used to the shape. Now C value is going to do a translation. This is the same as what you've seen before. So normally if I've got a minus something next to my x, it's going to translate the curve to the right, isn't it? If we're dealing with sine curves or rectangular hyperbola, whatever it is, we come along and we do x minus c, you know, exponentials, whatever it is. We translate to the right. Same thing here, okay? It's like you know, I've put a 2 in there. It's like all my x's have now, it's going to take them 2 more units before they get to where they were, right? So if we make that a negative number, I'll make it -2, then what we've actually got is x plus 2, right? So if I've got -2 there, it's like x minus -2, that's x plus 2. And that, I mean, by this stage of your maths education, I think you know this already, right? You know about curves translating left and right. So there's no surprises there. We want to keep it on 0, and then it looks like your regular y equals log x. Okay, I might leave it at that. I'm going to come back and do some questions from the book as well.